Okay, good morning, everyone. Welcome to the ICTP. My name is Yasser Iqbal. I'm from the Indian Institute of Technology, Madras in Chennai. I'm one of the organizers of this school and conference, together with Subir Sajdev and Shubhro Bhattacharjee, who unfortunately will not be able to join us for some personal reasons. So the great Hungarian mathematician, Paul Erdős, considered mathematics to be a social activity. He was described as a mathematical nomad who traveled from places to places and considered that mathematics should be a collaborative effort. And I think I was inspired by this quote and thought that why shouldn't this be extended to theoretical physics? Because ultimately, as Arnold said, mathematics is a part of physics. So it's a part of physics where experiments are cheap. With this, the goal of this school was actually to really get everybody together, working in diverse areas of condensed matter, quantum fluids, with a slight more emphasis on quantum spin liquids, and to have a lot of students here. So it's an advanced school, so there are a lot of graduate students that we were happy to have. And as we see that people are trickling in, the Budenich Hall is getting full. I think we have about a participation of 200 plus overall. So I hope that after this, the students would make friends with each other and continue their journey in physics. And it'll be great to have a nice interactive session with the speakers. And I think I encourage, and all of us encourage the organizers and others to engage with all the speakers of the 2 weeks over the span that they are here, and then try to make the most of this opportunity. In the spirit of ICTP, we also have, of course, participants from all over the world, from South America all the way from Japan, from north to south. And so I think it's a great opportunity to make also lifelong friends and collaborators, and I hope you make the most of this opportunity. With this, I think I'll basically open the conference, but before I do that, I would like to invite Misha Kiselev, who's our local organizer, and without which this activity would not have been possible, who's helped us a lot. And Misha, I welcome you to say a few words about ICTP and the other aspects.
Thank you very much, Yasir. Thank you, everybody. And welcome to ICTP, welcome to the conference. I think we will have opportunity to discuss many things regarding history of ICTP later on. And now, since we have 2 minutes before the first lecture starts, let me give you a few practical advices. So, my name is Mikhail Kiselev. There are 2 secretaries, Sarah and Chiara, whom you saw at the entrance. If you did not yet register in the lobby of Adriatica or Galileo, please come to them. They will be around during the first coffee breaks here. Their office is 115. This is on the first floor. If you need to see them in person and you don't find them around, please come to the office. If you need to solve some urgent logistic question, please write email to the email address which you all already used. This is SMR4114. If you need something which you believe requires my involvement, please write me email to mkiselev@ictp.it. Coffee breaks will be served just in front of the Budenich lecture hall. You will see it there. Lunches are in the cafeteria upstairs, 1 level up. Today we are going to have a welcome reception which starts at 6. It will be served in the same cafeteria. For those who stay in Adriatica and Galileo, you already instructed where to have breakfast and dinners, so you know that. If you have some questions, ask these questions. We are going to have 4 poster sessions. 3 of them are going to be in the circular corridor around Budenich Lecture Hall. 1 on December 9, when we have a Ramadan Prize ceremony in the afternoon, will be organized somewhere, likely in Adriatica Guest House, but we will send you this information later on. Practical advice for those who come from Adriatica: either you use a shuttle, or if you walk, please walk on the pathway along the tennis courts, not go along the route where cars go. This is dangerous, so when you cross Castiera, also please take care, look to the left, look to the right. Remember that you are in Italy. There is a special style of driving, so you just need to be careful, double careful, triple careful, because we need all of you staying with us. Again, if anything else, so Chiara is here, Sarah is here. The lectures are going to be recorded. The poster session booklet will also be available online as a PDF file. And at the end of activity, there will be certificates issued. There will be prizes for the best poster. So try to do your best. And if I miss something, yes, sir, tell me. Okay, I think we are almost perfect in time to start the activity. And let me give a floor to the chairman.
So, good morning. My name is Veka Assad, and I'll chair the first session. Sylvia is going to give a talk about quantum spin liquids, I guess. Correct?
Yeah.
And Yasia told us that we have to be social. So the idea is to ask questions, right? So you have to be social, you have to speak and ask questions. So please do. You don't need that.
I think I'm okay. All right. Well, thank you, Yaser and Fakir and Misha. It's great to be here. I was an organizer, or I'm still an organizer, but really the people you just heard from are the ones who did the lion's share of the work, so thanks a lot. And I wasn't supposed to speak, but anyway, some of the speakers canceled, and so I'm filling in. But hopefully you'll enjoy what I have to say. So I'm going to give an overview on quantum spin liquids, and the lecture today will be on insulating spin liquids. And lecture tomorrow will be on conducting spin liquids, meaning states you obtain by changing the density on the insulator to obtain either metals or superconductors. And of course, the subject of quantum spin liquids really started to become in the center of condensed matter physics with the discovery of the high temperature superconductors in 1986-87. Soon after, there was a suggestion by Anderson that this can be understood by an older state of his in Fazekas, something called the resonating valence bond state. Most of us didn't know what he meant by that. Probably he himself didn't, but he had an intuitive guess. This was a new type of state. And since then, of course, a lot has happened. We now have a complete theory of what you might call resonating valence bond states, or quantum spin liquids, and you're going to hear a whole lot about it. Many of them have been classified. You can look them up. There are different tables. There are different types of them. And understanding what are the different types of spin liquids is now a well-developed subject, and I'm sure you're going to hear a lot more, and I'm going to give an introduction to this topic. On the connection to the cuprates, well, that's kind of gone, I think, in and out of favor. Initially, there was a lot of work already in the 90s on how, starting from a quantum spin liquid, you could get high temperature superconductivity, but it seems to have faded away. But I hope to convince you it's time to come back, that there are some recent experiments which I don't see how you can understand them except by reference to quantum spin liquids. And really, a lot of progress is now possible on the experimental and theoretical side because we now have theories of insulating spin liquids. Okay, so that's now a real subject, and it wasn't when the cuprates were discovered. Also, it's worth mentioning, just to toot our own horn, ideas from spin liquids have changed other fields of physics. They are the foundations of quantum information theory, quantum error correction, and also many ideas in strongly correlated conformal field theories. They are really connected to ideas that came out of quantum spin liquids. Okay, so it's a very respectable topic to be working on, even though it acquired some disrepute for a few years. All right, so everything I'm going to talk about is drawn from this review article, which is on the archive, written with my former student, Maine Christos, Pietro, who will be here next week. I think he's giving a talk. Current student, Alex Nikolenko, and a former student, Avishkar Patel, who's now at ICTS in Bangalore. And also some parts are from this book. Okay, no more commercial announcements. All right, okay, so So the basic tool I'm going to use is something called the part-on method. This is also something that goes way back to the late 80s, but also acquired some sort of disrepute because people didn't quite know how to deal with it. But looking back, I'm firmly convinced this is by far the best way to proceed. And every spin liquid we're going to hear about can be understood by this method. Well, there are some fracton states, maybe not. I guess we'll see in the next lecture. But that's the approach I'm going to take. And it's a powerful method once you understand a few basic principles. So the basic idea of the method is to take some measurable operator, like the spin operator or the density operator, or anything that you can measure in the lab, and write it as the product of other operators. So you're fractionalizing the spin into some boson here, B, and the physical operator is the product of more than one boson. Okay, so this is just initially just a parameterization, but it's a very physical thing because we're going to now imagine that there's going to be a state of matter where these partons actually become physical excitations. They're real particles that are floating around. So it's the opposite of what happens in quantum chromodynamics. There you have quarks, which are unobservable, but we think of them as quarks being fundamental, and they form the proton. So you go from quarks to protons, that's the theory of quantum chromodynamics. Here we're going to go in the opposite direction. We just have spins, which are the analog of protons. And we're going to write the spins in terms of these partons, which will actually become real, can be measured in experiments in different ways. Okay, all right, so that's the general strategy. So one popular parton decomposition is to write the spin as a product of two bosons, sometimes called Schwinger bosons. And now we can ask what happens? Well, if you have ordinary bosons like helium-4, what can ordinary bosons do? Well, they can both condense and you get a superfluid. Now you ask, what's the difference with these bosons? Well, these bosons are not physical particles, and what that means is that they carry an emergent gauge charge. They carry a charge, there's a gauge field, and there's an emergent gauge charge that makes them unobservable because you can only observe gauge invariant quantities. So, the quarks have a color, SU3 color, and that makes them directly unobservable because you can only observe gauge invariant quantities. So what does this emergent gauge field do? Well, it changes the phases of the bosons to something else on this side. So in this case, ordinary bosons, when they condense, form a superfluid, whereas these partons condense, you just get an antiferromagnetic state. Now, sometimes under suitable conditions, bosons can pair. They can form a molecule, and then the molecule can condense. So similarly, both partons can do that too. And this is where you get various different types of spin liquids that I'm going to talk about today. The Z2 spin liquid, and also this U1/SO5 spin liquid. Okay, but that's pretty much all you can do with bosons, bosonic partons. But you could also, you're free to take your spin operator and write it as the product of two fermions. And which is the right way to proceed? Well, a priori, we don't know. The right way to proceed is the one that gives you the right physical excitations that you could measure in the lab. And without solving the Hamiltonian, you don't know which is the right way. So that's the weakness of the parton method. There's a little bit of guesswork, but with some combination of numerical studies and others, you can pretty much guess which is the right answer. So for example, now let's take fermions, fermionic partons. So electrons, which are ordinary fermions without an emergent gauge charge, they form a Fermi liquid when there's a finite density of them. In this case, you would get these, so these partons are called spin-ons. You get a spin-on Fermi surface, which is another possible spin liquid state. Electrons can pair to form a BCS superconductor, in which case you'll get a Z2 spin liquid. But now with fermions, there's many other possibilities because fermions can have topological band structures. The word topological, is overused, but here I just mean that even free fermions can move in a band with a non-trivial Berry curvature. So for example, if fermions from a churn insulator, then the corresponding spin liquid state when you gauge them is the Kallmeier-Laughlin spin liquid, sometimes also called the chiral spin liquid. If you pair them in a topologically non-trivial band structure, then you get Kitaev's honeycomb model. If you make them gapless like in graphene, then you get various other states on this side. So from this correspondence, you can build up, just about every state you're going to hear about in this conference, I believe. So my lecture today will be actually just on a small part of this. I'm going to really construct these states for you, show how it's all done. And one of the remarkable things that happens on the square lattice is that you can use either approach. You can use the bosonic parton approach or the fermionic parton approach. They end up giving the same state. And that's something took a long time to understand, but now there's a lot of evidence for it. And that's something now, as a theorist, you can use to your advantage to try and understand more complicated problems. You can also do it for the fractional quantum Hall effect, where you write the electron as a product of 3 fermions. You can get just about every fractional quantum Hall state that's been observed. All right, so that's just an overview of the introduction of what the parton method is. Now let me give you an outline of the topics I hope to cover. So there's 6 topics, 3 today and 3 tomorrow. So I'm going to begin very simply with just perturbation theory. This is something, Hartree-Fock theory of the Hubbard model, which is the basic model we want to understand. And then we'll go on to using the bosonic parton method to talk about quantum spin liquids, and the fermionic parton method to talk about somewhat different, but in the end not, quantum spin liquids. And then tomorrow I'll talk about what happens when you move these two will be insulators. I'll talk about what happens when you dope them. All right. Okay, so let me begin with spin density wave order in the Hubbard model. So I've written notes which are on the link I had earlier. And now I've just put all the notes up here, but I'll try to, it's in big type. I'll also use the board, and feel free to stop me anytime. All right, so I'm not going to read everything here. That's in the slides you can download. It's really like an article. But let's focus. So this is the Hubbard model. So you have fermions with spin 1/2 moving with some dispersion epsilon k. For now, I'm going to consider the square lattice. And this is the on-site repulsion on every side. So let's just take this model and just do the simplest thing, which is Hartree-Fock theory. But I'll do it in a path integral language to allow us to then do other things later on when we look at fluctuations more carefully. But let me just review what does Hartree-Fock theory say for the Hubbard model. Okay, so the way I'm going to proceed is I'm going to rewrite the Hubbard interaction after shifting the chemical potential a little bit as the square of the spin operator. Okay, and then you use the Hubbard-Stranovic transformation. You take the square of the spin operator and you write it as the integral of the operator P, which I'll call the paramagnon, in this way. So if you do the integral over P, you just get back this. This is an exact identity, it's just a Gaussian integral. You can complete the square and see you get this up to some normalization, which has been absorbed in the definition of the path integral over P. Okay, so what we've done now, as far as the electron is concerned, is that this operator here and this operator here had 4 Fermi operators. By doing the Hubbard-Stranovic transformation, this has only 2 fermion operators, it's P dot sigma. So now this is an exact rewriting of the Hubbard model. Now it's a path integral over the electrons and the paramagnon. This is the free fermion Hamiltonian. There's a P squared term, and there's this Yukawa coupling, as you might call it, between the boson P, which carries spin 1, and the fermions, which carry spin 1/2. This is not partons yet. There's no partons in this part of the lecture. Okay, and now the point is that at least formally, as far as the path integral is concerned, this path integral of C is completely quadratic, so I can carry it out. So I reverse the order of integration. Now I do the C integration first, and I get a theory for paramagnons, which is the determinant you obtain by doing the path integral over the C. Okay, that's a horribly complicated expression because P can be an arbitrary space or time dependence. So we don't know an explicit expression for it, but we can expand it to second order. So if you expand it to second order in P, you get P squared, you get this 3 over 4U that just comes from this term here, which comes from there. And then at second order, you get another contribution, which you can diagrammatically see is just the susceptibility. There's a P that emits a particle-hole pair, another P that emits a particle-hole pair. You evaluate this bubble, that gives you this Lindhardt susceptibility, and that's what goes in there. All right? And we know how to evaluate it. Okay, so now if I look at this number here, what I see is that if this number is negative, then P is going to condense. There'll be all of P to the 4th terms. So this is some kind of Landau theory for the paramagnon, and it's going to condense. But where is it going to condense? Well, that depends on the fact this chi naught is a complicated function of Q, and where chi naught is a maximum is where this would be the smallest, and the more likely that P will condense at that Q. So I'm just going to assume that this happens at the wave vector pi pi, which it does for certain band structures, and keep life simple. So we're going to condense P at the wave vector pi pi. Okay, so what happens then? Okay, so now we started with a metal. When U was very small, I just had a Fermi surface here. And now I'm going to condense P and ask what happens to the electrons. All right, so P is just going to acquire some expectation value at momentum pi pi. So as far as C is concerned, there's the free Fermion Hamiltonian, and there's this term, with this P is a constant at momentum pi pi. Okay, so then the effective Hamiltonian, so P is going to be just this. And at pi pi, this corresponds to antiferromagnetic order. So this means that once P acquires expectation value, if I measure the spin of the electron, it'll have this pattern. So it's a spin density wave state at wave vector pi pi. Okay, and the magnitude n can be anything, depends on all kinds of parameters. All right, so what is the Hamiltonian? Well, so you define this quantity delta lambda n, where n is the condensate of P, and you put it in here, and that shifts the momentum of the electrons by pi pi. So this is my Hamiltonian that I have to diagonalize. And this now involves diagonalizing a 2x2 matrix, because this will mix momentum little k with k plus pi pi. Then if you do it again, you'll go from k plus pi pi to k plus 2 pi 2 pi, but 2 pi 2 pi is the same, so you come back to k. So fortunately, it's only a 2x2 matrix to diagonalize this thing. Whoops. And so when you do it, here's the 2x2 matrix. This is the sum over half the Brillouin zone to avoid double counting. And these are the eigenvalues. So these being free fermions, all you have to do is just fill the lowest energy state, depending on the density of fermions that you have. So let me show you graphically how this works. Yeah, okay. Oh, sorry. Some of my slides have got mixed up. I guess I don't have those slides here. Sorry about that. Okay. I'll do it on the board. Yeah, there was a little error here. Okay, so let me just show you. So what we're doing is diagonalizing this thing. And these are the eigenvalues. So of course you can just give it to ChatGPT and it'll plot what I'm going to plot. But let me try to do it if you couldn't. So this is what you do. So imagine you have some Brillouin zone and you have some Fermi surface like this. So this is the locus of points, Ek equals 0. Okay, so now what this is going to mix with is with fermions with momentum k plus capital K. So let's also draw the locus of points where Ek plus capital K equals 0. And that means shifting this by capital K. And that'll give you four different Fermi surfaces. One here, and then another here. All of these dashed lines are the points where EK plus capital K equals 0. All right, so now if I look at this 2 by 2 matrix, there's some very special points. Look at this matrix. If this is 0 and that is 0, then because there's an off-diagonal matrix element, you're going to open up a gap. Just ordinary ripple repulsion. So this means that at these points, these very special points, which are called the hotspots, where these two intersect, you're going to open up a gap. So there can't be a Fermi surface because that's where the energy goes to 0 at those points, once delta is non-zero. So these are the hotspots. All right, so what is the Fermi surface going to look like? Well, you're going to open up gaps here, here. And so what you're going to find is that this little region is going to be its own little region here. There's going to be a little region here, here, and so on. So the Fermi surface will break apart or reconstruct in the following manner. So that's where these pictures were. So, so here's the original Fermi surface. Now this is the actual Fermi surface of the cuprates. It's a circle centered at this point. So these pictures here, I centered them on this point. But this is the K equals 0 for the cuprate sits at the center. Okay, so then you do exactly this procedure, and this is what you get, which are these little pockets that I showed you there. So the moment delta is not equal to 0, doesn't matter how large, immediately this big Fermi surface was split into pockets. Okay, and now what do the colors mean? Well, if you now look through the band structure, there are two bands here. And in the blue region, none of the bands are occupied. In the pink region, both bands are occupied. And in the empty region, one band is occupied. So the blue region is what we call hole pockets, because relative to one band, it's one less. This is what, so it means as you cross this line, you will see occupied states here and empty states there, inside. So if you have the empty states are inside of Fermi surface, you call it a hole pocket. And conversely here, this is in fact only one electron pocket. These four are part of the same pocket that sits over there. And the number of hole pockets is not 4, but 2, because this is your actual Brillouin zone. This has to do with this prime over here. You know, when I wrote this down, there's a prime. This is to tell you that you're only allowed to sum half the momenta, because otherwise you'd be double counting. This K and K plus K, you only want to pick any given momentum once. So the sum of the prime indicates that you only sum over momenta inside the diamond shape. So if you take the diamond shape, there's only one electron pocket and 2 hole pockets. Now, if you keep turning up delta, and if you're exactly at half filling, which is the case of interest for this lecture, then eventually these will also shrink to 0 and you'll get nothing. So now you have an insulator. So if the antiferromagnetic order is large enough, then you get no Fermi surface and you have an insulator. So that's the parent antiferromagnetic insulator. And lanthanum copper oxide is in this phase. It's at half filling and there is no Fermi surface. But if you could reduce the value of U, then you would get a metal. Of course, this is not seen in the cuprates, but something like this may well be happening in some of these twisted moire compounds in these days. Okay. Now, if you are not exactly at half filling, then no matter how large you make U, or the antiferromagnetic order, there will always be pockets. The electron pockets may disappear. This is for hole doping, but there will always be pockets. And the reason is that, well, you have to satisfy Luttinger's theorem, which says that the total number of occupied states must be given by the density. And if you just count up the number of states, if you're more holes than electrons away from half filling, then you can't get rid of the hole pockets. Okay, so let's see. And for electron pockets, electron doping, it's the other way around. So let me see. Here's the basic rule, which counts up how many states you've occupied. So you have density 1 plus P. P is how we measure. So let me put this on the board. So you have the total density equals 1 plus P holes, which is 1 minus P electrons. This is how it's measured for the cuprates. When P equals 0, you have an insulator, like I just showed you, 1 electron per site. You can put total of 2 electrons per site. So P can go all the way up to -1. P can go from -1 to 1. And the number of holes in electrons can go from 0 to 2. Okay. But P is generally pretty small and positive. So if you have 1 plus P holes, then you have hole doping. This is for P greater than 0. If you looked at the bands that I was talking about, I said there was one fill band everywhere. And relative to that one fill band, there are 2 bands really. And all we're doing is transferring. So you imagine one of them is filled, and then you're adding more electrons to the second band or removing one from the first band. So the 1 disappears. It's only the P, the difference from 1 we have to count once you've doubled the unit cell. So now, in this case, I've shown you for large doping, you get 4 such pockets. But really, there's only 2. And what's the area of each pocket? Well, so the area is going to be P over 4, where P is the doping per unit area. Sometimes you also want to, there's a factor of 2 pi squared here. So this is in units where this distance is 1. So this is the Brillouin zone. So you rescale here. This is called reciprocal lattice units. And the area of the Brillouin zone in reciprocal lattice units is just 1. So in that units, the area of this little pocket is P over 4. Now where does that come from? So here 4 is really 2 pockets times 2 spin. There's also a spin degeneracy. So there's only 2 pockets, like I said, because your Brillouin zone is shaped this way. So there's 2 of them, and there's 2 spin, and so this is what you'll get for P greater than 0. And for P less than 0, you have this little shape here. These are electron pockets. And now the area here is P over 2. And why is that? Well, there's really only 1 pocket. This is the same as that when you close it around. That's what I mean by a complete closed pocket. And this pocket is the same as that because they're shifted by a reciprocal lattice vector of the ordered state. Okay, so those are the simple things I wanted to get across about the ordered antiferromagnet. This is area P over 4. And this pocket here, when you close it around, is P over 2 for electron doping. And these are things you can measure. And in fact, in the lightly doped cuprates, this has been measured by photoemission, by quantum oscillations. These pockets have been seen at very low doping, and the area is indeed P over 4. Okay, so all of that works beautifully. All right, so what we see here, if I even go to half filling, is that I can get a state which is an insulator, but the insulator must have large magnetic order. Then I get an insulator. If I try to reduce the magnetic order, I go into a metal. That's what Hartree-Fock theory says. That the only way you get a metal at half filling is by, the only way you lose the magnetic order, it's the other way around. If you want to lose the magnetic order, then the only way you can do it, and that was the belief before 1980s, the only way you can lose the magnetic order at half filling is by going from an insulator to a metal. In other words, there is no way from Hartree-Fock theory to construct an insulator which does not have magnetic order. That's simply not possible. And what prevents it is precisely the Luttinger theorem. You just have to count states, and if you don't have magnetic order, then you have one electron per site, and there's no way you can avoid having a Fermi surface. Luttinger's theorem says you must be a Fermi surface, so it must be a metal. So the question is, can you get an insulated half filling without magnetic order? And Hartree-Fock theory says no. And not just Hartree-Fock, Landau, perturbation expansion to all orders tell you the answer is no. Okay, so this is getting an insulated half filling without magnetic order is a highly non-trivial thing. The answer, of course, is yes. And how do we describe it? Well, that's where the partons come in. The partons are the way you have to introduce partons to get an insulated half filling. Any insulated get a half filling without introducing partons is probably incorrect and not giving you a complete description. In fact, there's a theorem now, sometimes called the Hastings-Oshikawa theorem, that such a thing is not possible. That is, the only way you get an insulated half filling is by having a non-trivial state with emergent fractionalized excitations. So the quarks have to emerge in any insulator that doesn't have magnetic order. Okay, I think that's all I have to say for part one. Any questions? So this is a good time for questions on what I've talked about so far. Yes? Yes? Yeah.
The hadrons, the bound states. So could you precise the meaning of the words emerging in the framework of the Parton construction?
Well, okay. What I was trying to say about high energy physics, of course, what you said is completely correct. But one can imagine in high energy physics of thinking of the protons as fundamental. And you write down some very complicated theory of the protons. And eventually, out of the complicated theory of protons, you get a theory of quarks. Now, at high energies in that case. You have to follow high energies to go from proton to quarks. I think there are theories you can write down like that, this Kerr model with some topological terms are of that type. But they're very hard to analyze. But yeah, so we could have done it that way, but that's not the way the theory developed. It was much easier to go the other way. Imagine there are quarks which are free at high energies and then see how they're confined. So here we have spins, and yeah, but it's a little more delicate. Well, it's really have to go the opposite direction. If you go to very high energies, well, then you just see the spins. But you go to low energies, then there are quarks. But even though you're going in opposite energy, there's no fundamental distinction. That is, in our case, we are kind of forced to start from a theory of spins and get a theory of partons. But we could have also followed the same route for particle physics. That's all I was trying to say. So I'm just trying to throw cold water on the idea that quarks are fundamental. I mean, it's a very useful concept, but it's just because it's easier to work with. Oh, okay. I'm sure somebody will contradict me, but anyway.
So where were you? Yeah.
Sorry, it might be a naive question, but when you do the path integrals over the paramagnon fields,
Yes.
how do you assume that your fermionic path integral or the path integral over your C's is independent of your paramagnon fields?
All I'm doing is changing the order of integration. So initially, there's an integral over C, and then I just do the Hubbard-Stranovic transformation to have an integral over P and then the integral over C. So the only assumption is that I can do the integration in the opposite order. I'm not assuming anything else. Now, that may be not such a good assumption, but it's certainly true to all orders in perturbation theory. So my only assumption, it's an assumption, that I can interchange the order of integration, that's all. I'm not assuming anything else.
Thanks.
More questions? Willing to run around everywhere. Okay.
Oh, I can hear you. Yeah, fucker right here.
Here you go.
Why are you saying the patterns as quarks?
Well, because they're, in our case, they carry an, this is, we just pulled out this representation out of the hat. We just said the spin operator is what I can measure, but I can never measure this boson. It's nothing physical. It's just something, at least initially, it's something I write down to solve a certain problem. So these objects, I cannot do any experiment to create them. But what I can do is if you look at this, I can certainly hit the system with the operator S. And what's that going to create is it's going to annihilate one parton and create another one. Okay, so I can create a pair of them, a parton-antiparton pair. Now those, once I create them, they can move apart. And as they're moving apart, they could be infinitely far away. So then here I have a region with just one parton, where only one parton is present. And that's a very physical thing. If I want to describe spin transport, I want to describe neutron scattering, I have to take into account that there are these excitations in the system, which are essentially free particles. So there are free particles that exist in the system, but I cannot take them out. I cannot create them on their own. And what ensures that that's the case is by giving them an emergent gauge charge. And I only measure gauge invariant quantities. That's just a mathematical way of saying what I just said earlier. So the emergent gauge field and emergent gauge charges are very, very physical. They're simply accounting for the fact that you cannot create a parton on its own. Exactly the same is true for quarks. They carry this color gauge charge, and you can never create a quark on its own. You can create three of them, or a quark-antiquark pair, and so on. And at very high energies, it's as if they're free. In this case, they're free at low energies, not high energies. But okay.
So, also another naive questions. So, essentially, you said that there are three types of phases that we can get out of this picture.
Which picture?
I mean, the one with in which you condense the paramagnon
Oh,
field.
okay, yeah, not this, yeah, yes. Yeah, there are basically three, yeah, at half filling.
At
Yeah.
half filling, okay. And they are, and this behavior are robust under interaction, and this is, you
Yeah.
can say it because
what
of
is robust?
Ishikawa's theorem, essentially.
No.
Lattinger theorem, let's say.
Yeah,
okay.
so Lattinger's theorem will robustly tell you, will give you this result here. Yeah, this result. So there are some hole pockets, and there are some electron pockets. And Lattinger's theorem, and there's a value of P. And here I measure electron, you take the area of the electron pockets, electron hole pockets. P can have either sign, the areas are positive. Here I put the factor of 2 pi squared. So now this distance is actually 2 pi, not 1. Anyway, so the lattice spacing is 1 now. And this is Lattinger's theorem. So what we see here is that if your P is equal to 0, then you can also have A sub H and A sub E equal to 0. But if P is not equal to 0, one of these has to be non-zero. And in fact, the area is fixed. So all orders in the interaction, this result is true. When you have only hole pockets, the area must be P over 4. And when you have only electron pockets, for this geometry anyway, the area must be P over 2.
Okay, and
these are exact results for these metallic states.
Okay, and the insulating phase is obtained in which value of P for the insulating phase?
Only for P equals 0. You only get an insulator at P equals 0, but you only get it if delta is very large. So delta, you remember delta is lambda n. Delta is lambda n. Lambda was a coupling constant, which actually is just 1. Sorry, I have to correct that. Delta is just n. I'll fix it and just call it n, where n is the expectation value of the paramagnon field.
But so, and this is not an exact result that follows from Luttinger. This is like wisdom, let's say, that you need the
No, I mean, so
this expectation value to be larger to be an insulator. I'm trying to follow the logic.
Yes, so the exact state, the precise statement in this theory to all orders is not wisdom. The exact statement in this theory is that the only way you can get an insulator is if n is large enough. Or conversely, when n is 0, there is no insulator.
And why?
Because of the Luttinger theorem.
Again, okay.
Because, well, why? Well, so when n is 0, then the Luttinger theorem is a bit different. Then, you know, the area enclosed by this Fermi surface should be exactly 1 or 1/2. This area should be 1/2. So there has to be a Fermi surface because of the Luttinger theorem.
Thank you.
So there was one more question, and then we should go on, maybe.
So your integral goes from over. So my question is, do you work at 0 temperature?
Yes, yeah, these statements are for 0 temperature. Yeah, so of course in 2 dimensions, n will be 0 at any finite temperature because of low energy spin wave fluctuations. But I mean, the concept of a Fermi surface is also only defined at 0 temperature. There's no such thing as a Fermi surface at finite temperature. The singularity is only at 0 temperature. So yeah, these are, and even the distinction between a metal and insulator is only at 0 temperature. There's no formal distinction between a metal and insulator at finite temperature. Yeah. Yeah, at 0 temperature, yes. Why does this theory work? Sorry? No, I mean, so Hertz-Miller's theory, which I won't talk about, is the theory for this quantum phase transition. When delta goes from 0 to an infinitesimal non-zero value. Okay, so the framework, the Hertz-Miller's action is perfectly adequate for describing this. The initial Hertz-Miller's analysis requires further corrections that changes some of the exponents and so on. That's a very complicated subject I'm not going to go into. But the theory as a framework is perfectly okay. Yeah, so you right, so. No, I think if once you're at the quantum critical point, then by Hertz-Miller's theory, I really mean equation 4. I creep both fields around. This is a much better way to set up the renormalization by keeping both of them around. Yeah, and that's been done, and Lord is understood about it. But that's really a different topic. Okay, so now what we want to do, and the whole purpose of these lectures, is to now get an insulator at half filling when delta is 0. And we know such things can happen. There's a lot of evidence now in all kinds of models, computer simulations, and even experiments that this is possible. So I'm going to present the simplest mean field theories of such states. And the basic idea, which was already present in my initial slides, was, you know, when you're dealing with electrons or bosons, we have all these textbooks. We have all of Landau and Lifshitz on all kinds of perturbation theories we can do. So all you have to do is apply the same rules to partons, and you will get all the exotic phases. And that's the end of story, basically. But okay, there's a long story there. So for example, let me give you a quick picture of what this state is, this insulator without magnetic order. So for example, on the triangular lattice, you have a slightly different order, and this is seen in this particular material. But if you change the potassium to sodium, it seems to not have any magnetic order. And so the trial wave function that Fazekas and Anderson wrote down for this is the following. You imagine the spins on nearest neighbors form these singlet bonds. And so you pair them up in some way. And every such pairing is a dimer covering of the lattice. And then you take the linear superposition of all of these. So this is a exponentially large number of possible terms in the dimer coverings. If they're 10 to the 23 atoms, then you have e to the 10 to the 23 number of coverings. And you make a coherent superposition of all of them. Okay, so that's the resonating valence bond state, the sum of a huge number of such states. Today we say such states have long-range quantum entanglement. So nothing in Landau-Lifshitz has long-range quantum entanglement in that sense. So what are the physical consequences of such a state? Well, in fact, entanglement is quite hard to detect experimentally. If you look at this, you'll just pick one of them and you'll never know that there was this huge entanglement before you looked at it. So how can you tell that there's entanglement? And I think the key feature is fractionalization. That is, there are excitations which are particle-like but cannot be created by local operators. And each such excitation can be associated with what we call an anion sector. So in this case, for example, you can hit it with a spin operator that will change the system total spin by 1. So you have 2 spin-a-halves. And now these can move apart like quarks can move apart. In this case, they can move apart under suitable conditions, even at very low energies. And so now you're left with just one. This is the elementary excitation, which is one of the anions in this theory, which is a spin-on. So it carries spin-a-half and no charge. And no such thing exists in any previous state. Okay. So that's one of the anions in this state, the spin-on. In fact, there's another one, which was originally called a Vison, and these excitations appeared later in the toric chord. And what happens here? So what's a Vison? And we're going to construct that today. Okay, we'll see, in an actual theory. But this is the idea. You have some superposition in the ground state. And now all I'm going to do is change these coefficients a little bit. And how am I going to change them? They're going to pick a point and draw some branch cut. Doesn't matter which direction, out to infinity. And then I just count the number of dimers crossing the branch cut. In this case, there's 2 here, and 0 here, and 0 here, 0 here, and 1 here. So in this case, all of these C's remain the same, except C5 changes by a sign. This plus becomes a minus, and that's it. So that's a state, and if you're doing this, for an infinite cut, that gives you a state that's orthogonal to the ground state. And if you look at it, you can convince yourself that, these, you can resonate from here to there. So there's no problem really. The fact that there's a branch cut doesn't do anything because you have 2 of these resonating back to none of them. And so the 2 of them give you a plus sign, and so there's nothing. The branch cut is basically invisible, except at the end of it. The end of the branch cut is visible, and so that point is a particle called the Vison. All right, so those are the 2 simplest particles that appear in the simplest resonating valence bond or quantum spin liquid state. After that, things become very complicated, and we're going to see some of that. All right, so now let me build a theory of these 2 particles. Okay, and the simplest way to do that is to use the bosonic parton method. So what we're going to do first is map the Hubbard model to the Heisenberg model. So we are at half filling. So now P is equal to 0. And we have the Hubbard model, which let me write it only for nearest neighbors, C dagger I alpha, Cj alpha, plus U and I up, and I down. So on each side, there are 4 possible states. And there's the spin up state, the spin down state, the empty state, and also the doubly occupied state. Now, it turns out when you're at half filling, the chemical potential is such that these two states are much below the others. So this distance is very large, it's about a U. And there's a hopping matrix element between nearest neighbor site. There's a single site, which is T. So I won't go through this again, but there's a well-known canonical transformation. We can write an Hamiltonian on just the low energy states, which have no charge fluctuation. It's a spin-only model. And so this maps onto the Heisenberg model, J Si dot Sj, and J is equal to 4T squared over U. All right, so we're going to work with the spin-only model. We just assume the charges are gapped. So automatically, it's an insulator for free. So now our task is to just work with the spin-only model and ask, does this have a ground state on the square lattice which does not have magnetic order? Okay? And then we will have obtained immediately, if you can prove that there's such a ground state, we would have obtained an insulator that has no magnetic order. Because the charge part is already taken into account, we assume the charge gap is very large. All right, so what do? We represent the spin operator by bosons this way. And the way to think about it is right here. This is for general spin S. So if you have general spin S, there's two S plus 1 states. And you can just think of that state as the following representation. But more simply, for spin a half, there are two states, up and down on each side. And we write these as V dagger up of some fake vacuum. This vacuum doesn't really exist. It's the boson vacuum. So this is a physical state. And V dagger down is this. And you can do this for any S by that formula. And these are the only two physical states. So you have a local constraint that on every side, B dagger B up plus B dagger down B down must be 1. So you can also do this for higher spin. Then just all you have to do is substitute this and remember this constraint. All right, so that's it. So you take the original Hamiltonian, which is here. Then you make this decomposition. You have this additional constraint, which we will have to worry about. That's the key difference. And this is our Hamiltonian. Okay. So now it's a 4 boson Hamiltonian of canonical Bose operators obeying this constraint on every site. And all we're going to do now is, as I said, apply Landau-Lifshitz to this theory. Everything we learned for bosons from Landau-Lifshitz, we will now apply to this theory. There's just one important difference, but that's also somehow in Landau-Lifshitz. There's going to be a gauge field here. So if you run to the right volume of Landau-Lifshitz, you can also learn about gauge fields. But here the gauge field is going to emerge, even though it wasn't there to begin with. All right, so let's ignore that for now, and let's just go ahead and do a mean field theory. So Hartree-Fock says you just factorize everything in sight. We'll just do a very simple factorization. Now let me again, just like in the paramagnon theory, I'll set it up as a path integral. So I can write my path integral exactly in the following manner. The path integral over this spin system, so I'm doing a path integral over this Hamiltonian with this constraint. And I claim that's exactly this path integral right here. So you have these bosons, canonical bosons, as the canonical boson term. Then I introduce this field lambda, and this lambda, if you do the integral over lambda, I get exactly this constraint. I just give you delta function, B dagger B equals 1. And then there's this Q, another field Q. This is the analog of the paramagnon, which when I do the integral over Q from this term, I will get back this term. So just a Gaussian integral. So it's exactly the paramagnon trick. I'm now going to, of course, change orders of integration between Q and lambda and B. But this is an exact representation at this point of the original theory. So what are the important differences? One is that there's a local constraint with this lambda. Two is that this Q doesn't carry spin. It's spinless, because this object is spin rotation invariant. So that's the difference from the paramagnon. The paramagnon at spin 1, Q has spin 0. So if I condense Q, I'm not going to break spin rotation invariance. So it's setting things up to get a spin liquid type state. Okay. All right, but the most important property is that this theory, even though it doesn't look it, is a gauge theory. Because I can do this following transformation. You have to do a gauge transformation, in this case a U1 transformation, generated by this field rho I of tau. Rho I of tau could be anything. If you make this change and plug it in here, you will see that nothing changes. The action remains exactly the same. So this is exactly what happens in electrodynamics. You can do gauge transformation of the fermions in the gauge field, and the action doesn't change. So clearly there's a gauge redundancy to everything that I have to factor out. But I also have to ask another question. Now, we know that because of the gauge invariance in electromagnetism, we get a photon. There's an actual physical excitation, which is not a gauge artifact. It's a real photon with two polarization in 3 dimensions and one polarization in 1 dimension. That's an actual excitation that I can see as a consequence of the gauge invariance. So here, immediately, there's a question, is there a photon? Or if not, is there anything else which is truly gauge invariant, which is built out of the flux of the gauge field? So we're going to get something different here. We're going to get these emergent particles. In this case, on the triangle lattice, it will be the Wison. On the square lattice, in fact, there will be a photon. And we'll discuss how you tell the difference between them. Okay. All right, so first thing, okay, let's not worry about this. First, let's just do a mean field theory. So mean field theory, meaning we just fix Q and lambda to some constants, and then look at the Hamiltonian for B, which is fortunately quadratic, just like for the electrons previously. And you get some dispersion, you diagonalize it, and you find the best value of Q and lambda by solving the saddle point equations. So you do this on the square and triangle lattices. Sorry, this is very standard, BCS type theory for bosons. You go through all of the geometry, find the best values, and this is what you get. On the triangle lattice, these arrows tell you the value of Q, the orientation of Q. Q has kind of odd parity here, but the magnitudes are the same everywhere. And if you look at the dispersion, this is what it looks like for the boson. So you get these gap boson excitations, which carry spin 1/2, because the boson had spin 1/2. And so what's gone, basically you start out with some theory of bosons, B and B dagger, and then you do all kinds of mean field theory, and you get a very simple Bogoliubov Hamiltonian, some on K, some epsilon K, some gamma dagger K alpha, gamma K alpha, where gamma is some linear combination of B plus B dagger. So I just skipped all that analysis, which is very standard and familiar from BCS theory. And what I'm plotting is this epsilon K. So these are spin 1/2 bosons. S equals 1/2 bosons, which have charge 0. So my simplest, stupidest mean field theory in the parton approach has given me a theory of free particles. Free particles that never existed in physics before. These are bosons that carry spin 1/2 and have no charge. There's no such thing in any Landau-Lifshitz, because anytime you have spin 1/2, you have a charge. You can have spin 1, but then it'll be charge 0 or 1. You can combine electrons to make many things, but no one's actually ever fractionalized an electron before. But we have, anyway, when we got this theory of bosons, which is spin 1/2. All right, so now, do we believe this? you should be skeptical because there's all this gauge invariance and other things we haven't taken into account. And so we really have to think about, what about the rest? Is this mean field theory good? Okay, well, the answer turns out that it's actually pretty good on the triangular lattice, but not so good on the square lattice. It's not bad on the square lattice either. Okay, yes? Will it agree with some experiment or some numerical study? Is this a valid state for the square lattice antiferromagnet? It need not be, because I've done a totally uncontrolled mean field theory so far. Well, I'm considering some general Hamiltonian. Could I find some Hamiltonian in which this is a good state? The nearest neighbor model, yes, we all agree, has this order on the triangular lattice. Yeah, so the question is, everyone agreed this is a valid state on the triangular lattice. Now the question is this a valid state? Okay. And the answer is yes, it is. But which Hamiltonian and which compound is going to realize the state, I don't know. In fact, probably on the triangle, the recent evidence is that it's more likely that there's a U1 spin liquid of a different type. But on the Kagome, actually, this does work for certain Hamiltonians. But right now, I'm addressing more questions in principle. What I'm going to now discuss could be applied to any lattice. It's just a question in principle. What are the things you have to think about? All right, so what you have to think about is precisely this issue of what I've done here is put Q and lambda to some constant value. What about their fluctuations? Okay, so I have to now have a saddle point. Oh, yeah, one more thing I can say. The saddle point has a gap, either on the square or the triangular lattice. It can have a non-zero energy, so locally it seems completely stable. Now you could choose parameters so that the saddle point goes to 0. Okay, what happens then is, so this has a gap. So what happens when the gap goes to 0? Well, what happens then when you have zero energy bosons, the bosons will condense. Even in mean field theory, they'll condense. And that, in fact, is precisely, if you work it out, is precisely that 120-degree ordered state. So this approach can give back the state we all know and love, which is the 120-degree ordered state. It gives you exactly that ordering. But it also gives you this other state that we now have to check to see what are its characteristics. Okay, this is for the square lattice. All right, so we have to look at the fluctuations of Q and lambda about the saddle point and their constraints on them by the gauge structure. So this turns out to be a little more complicated than in the continuum for quantum electrodynamics. There it's very easy. You just say you have gauge invariance, so the simplest action is F mu nu squared. Then you just look at the wave equation for F mu nu squared, and you find a photon. That's how so I'm going to do exactly that, except I have to work on the lattice with a little more complicated gauge invariance. Okay, and then ask what happens. So if I look at the gauge transformation here, you see that it acts on the phases of the Q. The B's have gone, I've integrated them out because they had a gap, and shifts lambda by this amount. So it acts on the phases of Q and the constraint. So let me just only focus on the phases because the other parts don't care about the gauge invariance and they should be all okay. It's only the gauge invariance that can lead to something unexpected. Okay, so I define the phases as theta and as theta. Then this is the transformation on the lattice, on any lattice, on the square lattice now, excuse me. And now I look at this and I see these are both pluses here. So if I take a staggering, if I take theta ix is eta I times ax, and assume that ax and a tau are slowly varying, then this converts it to precisely the gauge invariance that I'm familiar with from quantum electrodynamics. So that immediately tells me that if I look at the low energy action of Q and lambda, hiding in there is the Maxwell action. Because that's the only action which at long wavelengths is invariant under this two quadratic order. So therefore, I have a photon. Okay. So this photon can have long-range forces, and it could take these bosons and then confine them, like quarks in a proton or quarks in a meson, really. So that could happen, and in fact, in 2 + 1 dimensions, that always happens because of monopoles, but I'm not going to go into that. So in the end, basically, the bottom line is that this theory on its own is unstable. And this spin liquid as a phase of matter doesn't really exist on the square lattice. Okay. So let's put that aside and go back to the triangular lattice. What happens on the triangular lattice? Now you have 3 different directions, 1, 2, 3, on directions. Where's the picture of that? Somewhere here. Oh, sorry. Everything is spelled out in the notes. Nothing is left out. Okay, you have these 3. I don't know, I don't have a picture of these EP. There's 3 different directions. So there are 3 different theta, and this is the gauge transformation of the theta. And so in Fourier space, it looks like this. So this is my gauge transformation now on the triangular lattice. And now you want something that's gauge invariant. Well, the only combination of the theta that's invariant under this transformation is this particular combination. So you have 3 of these combinations between 1, 2, 2, 3, and 3, 1. And so the simplest action has to be, wherever it is, I12 squared plus I31 squared plus I32 squared. Okay, but now you try to take the continuum limit to make, you want to make these thetas, you want to make these things depend on gradients. And you find you can't. And the best you can do is to make 2 of them a gauge field and the third one not a gauge field. Anyway, this is the decomposition you make. And when you put it in at low energies, you get this theory. So you get a theory which is not quite the theory of electromagnetism. What you get at low energies at certain wave vectors is this theory. So basically, first you have, of course, del cross A squared. So that's the electromagnetism. But you also have del A minus 2H squared. Okay, where have you seen this before? Well, this is what happens in the theory of superconductivity. Everything is Landau-Lifshitz, like I said. If you take a superconductor, if you have a superconductor with superconducting condensate psi, and you write it as e to the IH, then the low energy theory for this phase of the superconducting autoparameter is this. And we know what that does. That leads to the Meissner effect. It gaps out the photon inside a superconductor. And so that's exactly what's going to happen here. On the triangular lattice, it turns out that there's a Higgs field. So this H, it's called H because it's like the phase of a Higgs field. There's a Higgs field. And what it does is it breaks U1 down to Z2. And the Z2 has to do with this 2 here. It's just because you can still do it. There's still a gauge invariance left, but you change the sign of the boson. B goes to minus B. It's still respected in the ground state. And I'll just explain why that is in a few more minutes. Anyway, so the upshot of these calculations, which are completely standard, is on the triangular lattice you get a photon. So the triangular lattice looks like free quantum electrodynamics. Sorry, square lattice looks like free quantum electrodynamics, but the triangular lattice looks like electrodynamics in a superconductor, which is good because now you don't have any long-range forces. So these spin-ons have a chance. They don't feel each other when they're very far apart. If they emit a photon, it's totally screened by the condensate. in this case, these Qs in just the right way, so that they just can run away to infinity. So that's good. All right. So what I've shown you in a rather quick way, dirty way, is that if I perform this saddle point in the triangular lattice, then certainly to all orders in the coupling, I find a stable state with a gap with spin-a-half excitations. Okay, does that prove that this is a stable state? No, because the key word is all orders. All orders is not the same as exact. There can still be some other corrections which are exponentially small that could act up in the long distance limit. So we have to, what does that mean here? It means what I've done so far is, I have some big landscape of I have this huge space of Q and lambda, some gigantic space. So I have this huge space of Q and lambda. These are fields in space and time. And somewhere in there, there's a saddle point. I found a saddle point, which I've been studying. And near the saddle point, if I do some perturbative expansion, everything looks great. The forces are exponentially small, and I'm not going to get any infrared divergences at any order, and everything will look exactly right. However, that this is a path integral which I'm making an approximation with a single saddle point. The question we have to ask now, are there any other saddle points? Is this the only saddle point? Is there anything else? And in fact, there's an exponentially large number of other saddle points, and they could also kick in to destroy the stability of the state. So what are the other saddle points in this case to settle the issue? Well, the saddle points are topological. So we have to look at different saddle points of this action for Q and lambda. And what are they? Well, rather than taking the full theory for Q and lambda, I take this very simple Landau-Ginzburg theory, where I just take terms to fourth order. But now I have to remember that there's this gauge invariance, so I can only take product of Q around a loop, even number of loops. And I just take the simplest one with four links. So I integrate everything out and imagine that this is my free energy. And there's one saddle point that I've been working with where Q is all uniform. But are there any other saddle points where the Q's are not uniform? Well, it turns out there is one. And in fact, on a torus, this saddle point has exactly the same energy. But in this system, it won't because we're just considering an infinite plane. And it's this saddle point. So this is something numerically, just for that Landau-Ginzburg free energy, you can work it out. So what does this represent? So what this means is that you have the translationally invariant saddle point where Q takes some value everywhere. Now all I'm doing is writing down the change from that value. So the change is very large here, and it's become smaller and smaller and smaller. So there's a small region where the change is present, the magnitude. And then there's a change in sign along this line, where Q's have been flipped in sign. So this is precisely the Wison saddle point, which in the toric code is called the M particle. Appeared later. Okay, so there's a saddle point which is sitting at this point, and it just costs a little bit of energy. And the energy cost is only here, even though the branch cut runs out to infinity. So the branch cut is key because this is then also a fractionalized particle. I cannot do any local transformation of the ground state to get this saddle point, because I have to take the branch cut to infinity, or to the next Wison. So I can create a pair of these and then move them apart. And really, in the path integral, I have to sum, there's now, for every center, there's a whole infinite number of Wison saddle points. These are single Wison, and then you can have double Wisons. You can have a whole gas of Wisons. I have to sum over all of them to decide if the state is stable. Okay, all right. So how do you do that? Well, I guess I'm running out of time. You do it by simplifying the theory even more. You can show that the sum over the Poisson saddle points is equivalent to looking at a Z2 gauge theory. And that Z2 gauge theory, some version of it had been studied by Wegener, and by duality transformation, you map it onto the 3D Ising model. And then finally, you conclude everything is good. The stability of the high temperature phase of the 3D Ising model tells you that this is also stable. Okay. All right, I'm not going to go through all of that since I'm running out of time. But that's really how we know that the Z2 spin liquid exists. And it's called Z2 precisely because of this Z2 structure of the saddle point and the connection to Z2 gauge theory, which I don't have time to derive, but it's all in the book that I mentioned at the beginning. Anyway, so this is how, just by turning the crank with the part-on method, this is how this state was first discovered, by just looking at saddle points and then thinking about what kind of excitation they represent. So now I have a saddle point which has, I'll skip all of this. So I can write down a theory where I go from this non-magnetic ordered state, magnetic ordered state to this Z2 spin liquid. There's even a theory for this phase transition, which is well understood. And then we can ask, what is the structure of this state? So this state has these spin-on particles. So it has this, which are called the E particle in the toric code. And then it has this Poisson, which is called the M particle in the toric code, which has this branch cut that I just showed you. And what this means is that if I take an E particle and move it around an M particle, it's going to pick up a phase factor of pi every time it crosses the branch cut. That's going to give you a minus sign as it's moving around. So these particles, these anyons, the M and the E, the two, the Poisson and the spin-on, these are the spin-ons, are relative semions, because when you take one around the other, you're going to have to hit the branch cut. And then you can also imagine making a bound state of the E and an M. And if such a bound state exists, it need not, but if it does, then when you exchange them, you see you always pick up a -1 anytime you exchange them. So this bound state will be a fermion for self-statistics. So it's what's called the epsilon particle in the toric code. Okay, so that's the simplest spin liquid you can make. It appears in mean field theory on the triangular lattice, but it could appear on any two-dimensional lattice. And it has these three types of anyons, non-trivial anyons. The Poisson, E, the Poisson, which is M, the spin-on, which is a boson, which is the E, and then the bound state of the spin-on and the Poisson, which is called epsilon, gives you the third particle. And that's the complete characterization of the world's simplest spin liquid state with a gap. And this is how you could derive it if you just, applied the part-on method. This is how we originally derived it, but many people were skeptical. But I think after Kitev's toric code appeared, about 6 or 7 years later, the skepticism seems to have vanished, that this is actual state of matter. Okay. Questions? Yeah. Yeah. Sorry, where was that? Equation 27, you said? Which equation?
Yeah, this 27. So you took this mean field splitting B dagger, and BB. So
yeah. Well, I mean,
could be other ways. Can you comment?
You could also, you have to really look at, you could do more general. This is the minimal one. You could also have B dagger B.
Yeah.
And it won't change anything I said.
And both.
This is the simplest structure that gives you the answer. But you can include those.
All of them give the same.
It's give the same spin liquid. It'll change the numbers of it, but the structure will be the same.
Thank you.
The most important thing is you pick all possibilities that preserve spin rotation invariance, basically.
In the case of fermions, there is
Yeah.
this kind of not evident SU2 invariance of the fermion operators that still
Yeah,
leave the.
I'm going to, that's the next topic. I'm going to talk about that.
Very good.
For boson, there's no SU2 invariance like
There's
that.
only U1.
Yeah.
So,
yeah.
but then this issue of whether it's Higgs and U1, can you just tell by looking at the main field, like if there is B dagger,
Yeah, yeah.
B
So,
Z2, and if it's.
right, so it's exactly, the same question is completely equivalent to the following question. Yeah, you have this IPQ. So the question is, can you find a K such that this thing vanishes? Because both cos KQ over 2 and cos KP over 2 vanish. Can you find any such K? If you can, then you get a U1 theory. That's what in the square lattice you can. In this pi, that'll make it vanish. But on the triangular lattice, there's no way to make this vanish. No K at which this vanishes for general thetas. And that means there's always a Higgs field.
So just to understand, so if you go back hopping Hamiltonian effectively,
Yeah.
you would see the hoppings and no pairing of the bosons, or?
Right. I mean, it's ultimately associated to, another way to say it is that, you have some, pairing of the bosons. So on the square lattice, you have, let's call these 1, 2, 3, 4. So you have a pairing B, you have a condensate of B dagger 1, B dagger 2, and B dagger 2, B dagger 3, and so on. And so now from this, you can see that if I choose B on the even sides, going to the e to the I theta, B even, and B on the odd side, e to the minus I theta, B odd, that it doesn't change the mean field structure. So that means there's a zero energy mode, and if it varies spatially, you'll get a photon. On the triangle lattice, it's impossible to do it. So that's why there's this charge to a Higgs field there.
Very good, thanks.
It's really as simple as that for U1. For higher gauge groups, it becomes a little more complicated, but really that's mostly what the argument is. Yeah. So for the triangle lattice, there's still, the only thing you can do is change B to minus B on every site. And that's why there's a Z2 gauge invariance, and then a defect in that gives you the Wison.
Was a question
Yeah.
here?
Yeah. Yeah.
Did you mean that in a sense, like when you have an order parameter, you can either play on its magnitude or its phase? Is this the same?
Not quite, no. It's more like, what happens with the costless-Thouless transition. There we know that, if you didn't have vortices, which are the non-trivial topological saddle points, and then you have quasi-long-range order. And then you can ask, what are the vortices going to do? There's an infinite number of vortex saddle points. I have to sum over all of them. I have to solve the problem of the gas of vortices. This is almost very similar, except these are lines in space-time, okay? It becomes a little more complicated. And so what costless Thouless showed was there was a region where the vortices didn't do anything, and eventually there was a costless Thouless transition to where the vortices destroyed the quasi-long-range ordered phase. So it's analogous to that here, except you have one higher dimension, because you're not talking about points, but in space-time, they're lines in space-time. So you have to ask, are these lines in space-time? Can they proliferate and destroy this phase? Because there are all these saddle points associated with these lines in space-time. And the answer is no. And you know that because there's a duality mapping of this theory ultimately to the 3D Ising model. And the stability of the phase transition in 3D Ising model, which has been established by all kinds of arguments, tells you that this is also stable. But that's not an argument I went through. Yeah.
So first you start with a dimer lattice. so the dimer structure, which
Yeah.
you said is heavily entangled. So since you cannot really observe entanglement in real experiment, you look for quasi-particles that can be
Fractionalized
excited.
particles.
Right, you look for a fractionalized particle that can be excited on those states. And then you try to write a theory for those fractionalized particles, right?
Yeah.
And
I
from
mean,
there
the
you
dimer
get,
picture, of course, it's just a picture. You don't take it too seriously. But it's a very powerful picture which allows you to really think through what you're doing. But if you want to do an actual calculation, you have to do this. And, it's not nearest neighbor dimers. There are correlations of all types, and there are photons with power. All kinds of things are happening. But if you just want a crude, intuitive picture, use the dimer picture.
right, but like these quasi-particles that you defined,
Yeah.
So basically the idea, the first slide you proposed is that since we cannot measure the entanglement really, so for that purpose you're defining these quasi-particles that can be experimentally measured, or some part of their behavior
People have defined many other things. I'm not going to go into that, but people have defined various entanglement entropies. You can talk about degeneracy on a torus and many other things. There's a whole field of physics now with all kinds of measures of entanglement. Most are almost impossible to implement in any experiment. The ones I'm talking about, you can implement. You can look for these particles.
Thank you.
All right, I guess. Let me just quickly, since I have the slide, just quickly say what happens on the square lattice, and then, because I'm going to need that. So on the square lattice, we said there was a photon. Okay. All right. And then there's also, these bosons. So I have to couple the bosons to the photon. So I've done that here, and this is all way too much. Okay. Okay, that's another fun stuff. Okay, so you do that, you take some low energy limit, and you go through a whole bunch of steps. And when the dust settles, you get this very simple looking theory. This is called the CP1 model. It has a photon A mu coupled to a relativistic scalar field, Z alpha, with some higher order terms. And so now it becomes a matter of looking at the dynamics of this theory. But that's not the entire story. Then there are also these magnetic Dirac monopoles in the photons that are allowed. And so you have to put the monopoles in. And then a significant fraction of my life was spent on studying this theory. But when the dust settles, this is what you get. So what you find is the following, and this is going to play a role in my lecture tomorrow. There is a phase where you condense the V, just like on the triangular lattice, where you get this pi order. And then if you don't condense the B, because of these monopoles and all the photons, you get a state that's not quite a spin liquid. It's what's called a valence bond solid, where the spins form dimers or quadrumers, but the dimers or quadrumers crystallize in some pattern. There's not infinite resonance, there's only local resonance, but there's a preferred pattern. So there's a broken ground state degeneracy. But the interesting point for my lecture tomorrow is this point here. This critical point turns out to be a nearly conformal field theory, for which now there's quite a bit of evidence, which is ultimately unstable to either of the phase, but over very long distances. There's a very non-trivial conformal field theory that emerges here. I don't know, maybe someone will talk about it later in the school, but or the conference. I'm sure you're going to hear some talks about this critical point. But that's been a huge subject with lots of studies, and but finally theory and numerics and even experiments in some cases coming together to this non-trivial critical state, which is actually also described by the fermionic approach, which I will say something about tomorrow. That's exactly on time then. That's right, 10:30. Any more questions on the square lattice? Or, okay, let me just throw in one little thing on the triangle lattice, if you don't mind. So one thing I didn't talk about is, I told you about this Vizon. Here's a Vizon particle sitting here at the red, okay. All right, so you think it's a kind of a trivial thing, but imagine the Vizon moves around. So it moves around and goes there, and comes back. So this is the kind of thing you would do to compute a Berry phase. You take the Vizon and have it move around. Now, when you notice it comes back, the branch cut is different now. Initially, the branch cut was running this way, but now there's an extra loop. It leaves behind a trail of the branch cut. So that means that the phase of the wave function has changed because of this trail. And you can get rid of the branch cut by flipping the sign of V on this side. So this means that the Vizon actually sees a flux, and it's moving around, flux pi around every site. So that's what makes this what's called an odd Z2 gauge theory, not exactly the gauge theory that Wegener, a particle physicist, studied. And then we proposed a theory that includes the spin-ons, which are the Z's, small z's, the capital Z is the Ising gauge field, and then there's this Berry phase for the Vizons. And you can put it all together and put this on a computer, which is what my student Shackleton did. It should be a reference here, and obtain this phase diagram. This is the Z2 spin liquid in the magnetic order. And because of these Vizon fluxes, you also get a valence bond solid phase. And all of these three phases are seen in different systems. And what's happening out here is still an open problem, and I think you'll hear more about it from other lecturers. Okay, I'll stop there.
Further questions? Comments? Yes. Just wait 2 seconds.
So hi, thanks for the nice talk. The part on mean field ground state is a Slater determinant of the B operators, right?
Well, it's bosons. It's not a Slater determinant. It's a permanent or something.
Yeah.
Okay.
So now this has short range entanglement. How do I get back the long range entanglement of the actual valence bond ground state?
Well, so it depends. You have to define what you mean by long range entanglement, I guess. I mean, certainly when the bosons have a gap, it's certainly true that all correlations decay exponentially. But this state has a topological entanglement entropy. So if you look at the entanglement entropy of a given region, no matter how large, that's why you call it long range, then there's a part that's related to the surface area, but there's a constant. Mm-hmm. So that constant is related to the fact that there are all these topological excitations. So you have to put in the Vizons in the wave function. You can write down wave function with the Vizons in them, and you have to look at their contribution. That was not done in this language by Preskill and Kitaev. And so there is you have to put the Vizons back in.
Okay, okay. And one more question is, this might seem very stupid, but then how do you, in what sense is it a liquid? Is it because we are not breaking SU2 invariance, or?
Or translation invariance, yeah, that's why it's
liquid.
Yeah.
All right.
It's liquid, yeah. Maybe you define a liquid as opposed to a gas, if you mean. It's very dense. There's a boson on every side. So that's but it's not of particles, so let's call it a liquid.
Is there a way to see from the continuum what all the possible phases are? Like to see that a Z2 spin liquid or this nail VPS are the possible phases?
I think the hard part is knowing how to take the continuum limit. And there's given some Hamiltonian, there's many different choices you have to make to take a particular continuum limit. Once you've taken the continuum limit and have a field theory, as I tell the particle physicists, the rest is easy. I just have to look up some book what the field theory does. The hard part is making the connection to the right field theory.
Is there a way
you're making some guesses there.
Is there a way to catalog the possible continuum field theories? Like from a given well, maybe not from a given Hamiltonian, but just from symmetries.
Full catalog. I mean, you could say, there's a field theory written on the board outside, You have some fermions, you have some gauge fields, and you have some Higgs fields. Almost everything can be written that way. Yeah. Yeah, so that's a catalog if you wish. And there's also Chern-Simons term that's missing out there. So there can be various Chern-Simons and other topological terms. Anomalies, that's actually probably the hardest part, is knowing exactly what the anomalies are. For example, this thing that I showed about here, this, you know, this phase factor for a Wison moving in a ring, that is apparently some anomaly. And when people in algebraic topology tell me what it is, I have no idea what they're talking about. But this is an example of an anomaly. And that has to be built into the structure of your field theory. And that's not easy. In fact, so for example, we wrote down this lattice model here. This one. This is on the, it's not a continuum. And then we simulated it. And from the simulation, we found these three phases. And now we can ask, what about this? Is there a field theory here? Yes, we know the answer to that. It is a certain O4 field theory. We know the field theory here, and we don't know the field theory here. Now, there's a conjecture that this field theory is actually a theory of Dirac fermions coupled to U1 gauge field. Just comes from a lot of numerical work. And we know for sure that field theory has the right anomalies. But how to derive it from this approach, yeah, I think that's one of those basic open problems. On the square lattice, that connection has been made between different approaches. I didn't have time. I thought I'd talk about it, but I'm already over time.
Good, so I think we can thank Subir again. And we have a 30 minutes break, so we start at 10 past. Is that okay?